In this video, we'll begin to consider financial math by looking at the concepts of simple and compound interest. First, let's introduce some terminology. Principal refers to the original amount invested in an account, while interest refers to money paid by a borrower to a lender in return for the ability to borrow money, and it's usually expressed as a percent of the amount borrowed. Now, simple interest describes when interest is earned only on the original principal. Here's an example. If $5,000 is invested for 4 years at 5% per year simple interest, find the amount earned in the first year. Now note this 5%/A stands for per annum, and it means that that's the annual percentage rate of interest. Sometimes that's also abbreviated instead as APR instead of /A, APR for annual percentage rate. So if we want to find the amount earned in the first year, then we take our 5% and express it as a decimal and multiply it by the principal, because we're going to get 5% of $5,000 earned in the first year. If we multiply that out, we get $250. Now, because it's simple interest is only being earned on the original principal, it doesn't matter what year we're in, we're always going to earn the same amount. So $250 is the amount earned in each subsequent year as well. If we look at this as a table and start with $5,000 at the beginning, we can fill in the amounts in the account at the end of each year. So at the end of the first year, there's going to be the original $5,000 plus another $250 is $5,250. At the end of the second year, another $250 will be in the account, making it a total of $5,500. At the end of the next year, there will be $5,750. And finally, after 4 years, there will be a total of $6,000. And all we're doing each time is adding $250. That's the case of simple interest. If we look at the amounts then in the account at the end of each year, we can see that they're going up by a common difference of $250 each time. That means that these numbers, the amounts, form an arithmetic sequence. So in answer to the question, what kind of sequence do the total amounts form in the case of simple interest, we can see that they form an arithmetic sequence. Another way of looking at that is as a function, and we've seen previously that arithmetic sequences form linear functions. Those are two different ways of looking at the same thing. If we're looking at how the amounts go up, they're going up as a linear function like that in the case of simple interest. To go back here, as the year goes up by 1 each time, the amount is going up by a constant amount, 250. That's characteristic of a linear function. Now let's look at compound interest. Compound interest describes when interest is earned on the original principal and on any previously earned interest. This is different from simple interest, where we don't earn interest on our interest. So in compound interest, we earn interest on the original principal and on any previously earned interest, and this is usually how accounts work. Let's look at a similar example to the one we saw before. If $5,000 is invested for 4 years at 5% per annum interest, but this time it's compound interest, find the amount at the end of each year of the investment. So we start off again with $5,000. Now, to figure out how much money we would earn in the first year, we would do the same thing as before. We would multiply $5,000 by 0.05, and that would give us $250. But if we wanted in one step to find out how much money is left in the account, instead of taking that and adding it to 5,000, we could just do that all in one step by taking 5,000 and multiplying it by 1.05. The 1 is going to give us back the amount we started off with, and the 0.5 will give us our interest. And if we do that, we get 5,250 right away. So to get the amount left in the account after 1 year, we multiply by 1.05, and we have 5,250. And that's just the same as we saw in the simple interest case. But now, to find how much money is left after the next year, because we are now earning interest on the whole amount in the account, we are again multiplying by 1.05. And this time we get $5,512.50 left in the account. 5,250 times 1.05 gives us this number here. And now we can see that this table is starting to differ from the simple interest case. If we multiply by 1.05 again, we get $5,788.13, rounding to the nearest cent. And then after one more year and one more multiplication by 1.05, we have $6,077.53. And you can see if you compare this to the simple interest table shown here, that we've come out about $78 or so ahead in the compound interest case if we are the one with the investment. So the difference again is that here we're earning interest on our interest. If we look at the amounts and ask what kind of sequence they form, we see that instead of going up by a common difference that we're adding, now they're going up by a common ratio that we're multiplying, and that's characteristic of a geometric sequence. So in answer to the question, what kind of sequence do the total amounts form in the case of compound interest, they form a geometric sequence. And as we've seen, a geometric sequence traces out an exponential function because exponential functions also have this pattern of multiplying by the same amount each time you step up one to the right. So these would be the y values of an exponential function if the years were the x values. So in the case of compound interest, amount is a function of time and it's an exponential function. In contrast to the simple interest case where we saw it was a linear function. So compound interest, we'll see the amounts go up more like an exponential function, like that. A bit more terminology now. Future value refers to the amount in an account at some future time, and future value is abbreviated FV. We often use the word amount to mean the same thing, and so we'll abbreviate that with A. Whereas present value means the amount at time 0, now, or the principal. So that'll be abbreviated PV for present value, or you'll see it abbreviated as P for principal. Here's a question where those are used. If $100 is invested for 25 years at 3% per annum interest compounded annually, write an expression for the amount A at the end of the investment term. So using the pattern we saw before, the amount in the future is going to be equal to the principal, $100, and we're going to multiply that each time we step to the right by a year by 1.03. And we're going to be stepping to the right on the chart 25 times for the 25 years. So we take 100 and we're going to multiply it by 1.03 each time for 25 times. This number here is the principal, or the present value. This number is 1 plus the interest rate, and the interest rate is expressed as a decimal. So in this case, 1 plus 3% expressed as a decimal. And the number in the exponent, the number of times we're going to multiply it by, that's the number of compounding periods. And in this case, there's 25 of them. It's not strictly the number of years because, as we'll see shortly, we could be compounding more or less frequently than a year. So think of this as the number of compounding periods. If we get more general, we can ask if P dollars are invested for N years at I% per annum interest compounded annually, let's write a completely general expression for the amount A at the end of the investment term. So now we've replaced 100 with P, 25 with N, and 3% with I%. So we just replace them all correspondingly in the equation, and we get the amount is equal to the principal times 1 plus I to the power of N, where I is expressed as a decimal. Now let's look at compounding periods other than 1 year. Although interest is typically quoted as an annual percentage rate, which we've been abbreviating as APR or showing as /A per annum, it's often compounded on a different non-annual time period, and we need to take that into account. What it means if it's compounded differently than annually, let's say it's compounded monthly, as down here in the bottom of the table, that means that once a month, the bank or other institution paying out the interest is looking at how much is in the account, calculating an interest calculation, putting that interest into the account, and then doing that again the next month. That's going to give us a different result than doing it once a year. So we need to think about the interest rate per compounding period and the number of compounding periods. You can imagine that if you have an account paying 6% per annum interest, and you are compounding semi-annually, that is twice a year, then that means the account is actually paying 3% interest every 6 months, rather than really paying 6% interest per year. So we need to think about the interest rate per compounding period, as well as the number of compounding periods. If you're compounding semi-annually, that's going to be 2 compounding periods per year versus compounding annually, which is only 1. If we go back to this expression, remember we said that this number here is the number of compounding periods, not the number of years. And this interest rate here is the interest rate per compounding period. So let's do an example. Given an investment of $100 for 4 years in an account paying 6% per annum interest, find the expression for the total amount at the end of the investment given each of the following compounding frequencies. And then let's simplify to find the dollar amount. Annual compounding is what we've been looking at so far. So that's just the same calculation. If we start with $100, each year, if it's 6% per annum interest, we're multiplying that by 1.06, 1 to get back the original amount, 6% or 6 as a decimal here to get the interest. And over 4 years, that's going to happen once a year, so that's 4 times. If we put that into our calculator, we get $126.25. However, if we change the compounding frequency to semi-annually, that means every 6 months the bank is paying out 3% interest because we get 0.06 is our interest as a decimal every year, but we're dividing that by 2 to get our 0.03 interest every 6 months. And the number of compounding periods is not 4, but it's going to be 8. Therefore, we have to change this, and we get 100 times 1.03, because that's 0.06 divided by 2, to the power of 8. And if we do that calculation, we see that we end up with slightly more, $126.68 at the end of the investment. If the investment compounds quarterly, that's 4 times a year, then in 4 years that's going to be 4 times 4 or 16 times. And instead of getting paid 0.06 each year, we're getting paid 0.06 divided by 4 every 3 months or every quarter of a year. So we can write that. You can either work that out or put it all into your calculator like this. 1 plus 0.06 divided by 4. That's what we did here. 1 plus 0.06 divided by 2, and then the 16 goes up here in the exponent. If you work that out on your calculator, you get $126.90. And then compounding monthly, 12 months in a year times 4 years, that would be 48 month-long compounding periods. Each month-long compounding period, we're getting 0.06 divided by 12 as our interest. So we would write that as 100, our principal, times 1 plus 0.06 divided by 12 to the power of 48. And you can let your calculator do this for you all in one step if you like. And you get $127.05. So you can see that with the same per annum interest rate, increasing the compounding frequency will increase the total amount of interest paid. And that makes sense because we're earning interest on our interest. So the sooner we get that interest into our account, the more opportunity we have to earn interest on it. Now you can also do calculations like this on your graphical display calculator. If you have a TI-83 or 84, you press the Apps button, go to Finance, and then choose TVM Solver. TVM stands for Time Value of Money. You enter the values that you know, and then press Alpha Solve on the row to find the value that you want, the one you've left blank. You need to follow a convention where cash flow out is negative. Cash flow out would be something like taking money out of your pocket to make an initial investment. And cash flow in, money coming into your pocket, is positive, and that would be something like an investment coming due. You need to be careful also with this because if you neglect this, you'll get an error message. Here's an example. Let's use the TVM solver to find out how much money we would need to invest today to have $100,000 in 40 years if the account paid 3% per annum interest and it was compounded monthly. So we go to Apps and then choose Finance and then choose TVM Solver, which is the first one. And you'll get a screen that looks something like this. If there were already values in any of these, they may not be zeros, but that's okay. We're just going to overwrite them anyway. So we want 40 years of monthly compounding. That's going to be 480 compounding periods, but you can also just put in 40 times 12 into the n, and it will do that calculation for you. N is going to be your exponent. I% is the interest per compounding period as a percent. So it's 3% per annum, but there are 12 compounding periods. So we need to do 3. Remember, it's as a percent, so we don't do 0.03, we just do 3 divided by 12. That's going to be the monthly interest rate. And again, we can let it calculate that for us. Present value is how much money we need to put into the account now. That's what the question is asking. How much we need to put in now to have $100,000 in 40 years. So we're going to leave that as 0 and come back and solve for that row. PMT stands for payment, and that's asking how much money we're going to be putting in regularly. We're not going to be putting any more money into this account after the initial investment, so we leave that 0. This is something that we'll look at when we get to annuities. And future value is how much money we want to have at the end. And I'm moving up and down between these rows by pressing the up and down arrows. So we want 100,000 in the account in 40 years. So I'm going to make that 100,000. P/Y stands for payments per year, and C/Y stands for compounding periods per year. PMT and begin refers to whether the payments happen at the beginning or the end. All of these three things have to do with annuities, and we're going to leave those be. So we're just going to deal with these first 5 rows here. We filled out the 4 that we know, and we're going to go up to present value, press alpha, and then solve, which is the enter button. And we get negative $30,164.56. So that's the amount that we would have to put into the account now. It's negative because it's a cash outflow in order to have $100,000 after 40 years of monthly compounding. So that's the answer to our question. That's how much we need to invest. We need to invest $30,164.56 now in order to have $100,000 in 40 years. So that's an introduction to financial math and simple and compound interest.